Hello everyone. In this lecture, we will see what is meant by equal a priori probability. To do this, I will be going to follow the R.K. Patria book. In statistical mechanics, when you take this chapter, the first question arises why we need statistical mechanics. Because from thermodynamics we can achieve any property that can be temperature, pressure of a room or a system. Because if you have asked by someone to measure the temperature of this room, you just have to pick up a thermometer and see the reading, and you will say the temperature is 43 degrees centigrade. But how this temperature can be measured using thermometer? The process is explained by this statistical mechanics. Statistical mechanics takes the microstates average behavior. The macrostate means the system, and in that system there could be many configurations. The many configuration means the particles inside a system can be arranged many different ways to externally shows the same system. We don't know what inside our body, but at the output we know each faces. But inside our body there could be any arrangement, and using many arrangement there could be the same face, same external behavior. That is meant by microstate of a macrostate. If a system, let's consider this box is a system having number of particle capital N, energy capital E, and volume of this box is capital V. So this energy, volume and number of particle, although volume is fixed, but we can shape this box like this. Still this volume can be capital V, number of particle can be N, energy can be capital E. So to satisfy the same number of particle, energy, volume, we can have many configurations. That is meant by microstate of a macrostate. So microstate is microscopic behavior and macrostate is overall behavior. If you look this copy, this is a copy. But if you look closely, this is a statistical mechanics copy. So that's how you can define macrostate and microstate. Due to some technical problem with microphone, we have lost the voice of previous video. That's what I have done here. So let's try it again. First of all, to know about equal a priori probability, we have taken a system whose number of particle is given by 4, energy given by 6 epsilon. We can achieve this 6 epsilon energy by these 4 ABCD particles in different ways. First way is place this A and D particle at zero level. Particle A staying in zero level means particle A having that level's energy. You can sit in a level if you have that amount of energy or degree. You can't sit in your teacher's chair. That's you don't have the power or position. If particle A is sitting on zero level, that means it has the energy of that level. So A, D having energy 0 because this first level having energy 0, second level having energy epsilon, third level 2 epsilon, fourth level 3 epsilon. You can choose any energy for any level. To explain the equal a priori probability, we are considering that. So let's consider AD having 0 energy, CD having 3 epsilons amount of energy. So at the net, what we have the total energy? C having 3 epsilon energy plus B having 3 epsilon energy. Overall 3 plus 3, that is 6 epsilon energy. The condition is satisfied. So this is a distribution. This is a microstate of this macrostate. But this microstate can be achieved in different ways. That is, this A can be at last level, that is level having energy 3 epsilon. If A is there, C would be here. By replacing these particles, we can achieve the same 6 epsilon amount of energy. That's what we have done using this calculation. If you are capable to do these things with your imaginations or pictorial representation, you can do that. But we have a simple formula. Using this, we can get the number of ways by which this can be achieved. So this is the formula. We have placed the number of levels or number of ways factorial at the numerator, and at the denominator we have, because in zero level we have two particles, so we have multiplied 2 factorial, and here we have 0 factorial and 0 factorial. 0 factorial equals to 1, so we have no meaning to put 0 factorials. That's why we have done only 2 factorial times 2 factorial. If you do these calculations, we have 6. Similarly, for this distribution, we have find the number of ways is 24. If you do these calculations for all this distribution, we will have this number of states, this number of ways. 42 is number of ways for this distribution, where ABCD achieving at each levels, means one particle is at one level. So this is the more probable state, because it has the number of distribution compared to others. It has the more number of distributions compared to others. Because if you look at this, system at any particular time, there would have more probability to see the system at this microstate, because this having low values, these distributions having low values compared to 24. If you look any point of time, there would be absolute that you will see this distribution, that all the particles are sitting in 1 levels. They are separated to each other. This is what this graph is showing, and if you take number of particles in the order of Avogadro number, in that case this peak will be more sharp, means the peak will be like a Dirac delta function. For a particular microstate, there will be a peak sharp and other values will be saturated around 0. That what we have discussed in our first talks, that is, if you look this room's temperature, the molecules or particles could have any amount of kinetic energy, but most of the particles having a certain distribution. That's why we see the temperature of this room as 43 degrees centigrade, but it could be anything, because all particles are known in single state or single microstate. All the particles could have a state that can give us a temperature 0 Kelvin, but the probability of getting that is too small, that overall we are seeing the temperature as 43 degrees centigrade. You see what's the difference between thermodynamics and statistical mechanics? It's a big tool to deal with the macroscopic behavior using microscopic details of the environment or universe. We are dealing with lots of particles with accurate, using the probability and the distribution concept. And in the next lecture, sorry, I have not mentioned you the equal a priori probability. That is, if you have the system having lots of particles and we have no constraints. In this case, we have applied constant that the number of particles is 4, energy is 6 epsilon. If you don't have any constraints, in that case, the solution of Schrodinger's equation for that system would have very large number of solutions, and each solution is a microstate, and each microstate have equal probability to appear at the output of the system. Means at the output of the system, if this room will have no constraint, in that case we could see 0 degree centigrade and 43 degree centigrade with equal probability. All temperature will have equal probability if we have no constraint, but if we have constraint, the walls are making constraint about this room. So using all those constraints, we will have a for single state for which the distribution is maximum, called the most probable microstate. And if we have no constraint, in that case all microstates are equally probable. That's what is equal a priori probability. Again repeating this, if we have no constraint, there would have a single microstate which will be more probable than any other state in that macro state, but called the most probable microstate. That's what is most probable microstate. But if we have no constraint, in that case all the microstates, means in that case the probability will have a this kind of line, all probabilities will be same. That's what mean by equal a priori probability. So that's all for today's video. Although this could be a little helpful for you if you are trying to understand the concept of statistical mechanics, equal a priori probability. I think so. If it is, feel free to like this video, give any suggestion or recommendations you are thinking of, and if you like to continue with our series of statistical mechanics, feel free to subscribe this channel. This is free of cost. Thank you. See you in our next lecture.